Uh, Hello everyone. Am I audible?
Yes, sir.
Yes, you're
Yeah.
good. Good evening.
Good evening. So this week we are generally will be studying about the batch normalization and some training tricks. I mean, we have already discussed most of the thing. A few things are there, that is the batch normalization, and that is also more like a story like things in which you can simply understand using the simple logics. So nothing much this week. Have you watched those videos?
Not completely, sir.
Yeah, completed, right? So yeah, let's see if you have any doubts. I will repeat few things. Yeah, so the idea of batch normalization came from the batch training, right? Like let's say when you are doing stochastic training, every time you are giving a input and you are training for it, and then the next time you give the input, the overall uh, variance of the input has, I mean, the mean and the variance of the input has changed, and then your network has to adjust itself for the second input, which is totally different. Like let's say somewhere the first input is a white horse and the second input is, in the second iteration, your input is some red flower, the red rose. So basically, even if there is a classification problem, the neural network has to go for a very long iterations to converge, and still not very sure if the test loss is going to be smaller or not. And also there is a chance that if the network is o- uh, overfitted or underfitted, right? So these are the basic things that the normalization solves itself. So and that's where this topic comes in. So let's see. Let's do some little bit of mathematics. So you have an input. Yeah, you have inputs that is going from I to equal to 1 to n, and in which let's say you are training for 10 type of classes, right? Either what can happen, let's say if you are training for 10 type of classes, and for each class you have let's say 100 uh, uh, train plus validate plus test samples. So overall, you have 1,000 samples. With it might happen that the mean of each class are much different than the mean of the other class, right? So mean of classes, like let's say if we will do a simple classification problem, or if you will plot a simple embedding in which you might see that one of the class is lying somewhere here, another class is lying somewhere here, some other class will be lying somewhere here, right? Like let's say if you are doing an autoencoder training, autoencoder, in which in your latent space you have this input, and then let's say you have a two latent space here, and then you are reconstructing your output. Then if you will, let's call it Z1 and Z2, and if you will plot the Z1 and Z2 for all the input you will give after training, they will create a cluster such that this Z1 versus Z2 will create 10 different clusters in which you will see that the each cluster is basically are the different uh, classes. Class 1, class 2, class 3. However, these are the embeddings or the latent space. In the similar way, you can imagine that if you are going to take the mean and the variance of each class, they will be very different. And when you are giving input without thinking at from which class it is going to enter into the network as an input, then the variance will be shifting each time, and then network is going to face the training problem, and you can say the problem of convergence, right? So I hope the motivation is pretty clear, right? So what we are going to do, we are going to say that we are going to give this network inputs. However, the network is going to take another input, the transformed input, that will have a mu and sigma, which will be pretty much not changes with this input. I will change. It has, let's say, mu I, sigma I, or something like this, and then this is going to be in the net into the neural network. And then whatever we are if you are doing the classification, then you will have a classification as output, right? So we are saying that we want this to be constant. Okay. So we are saying that every time we are taking this input, we are recording this mu and sigma, and these are the xi, and we are calling this mu and sigma, and then we are calculating this xi minus mu by sigma, and then let's call it something k, and then we are creating this yi that is actually equal to mu I into xi plus sigma k. Okay, so we are saying that if this is my input to the network, my training is going to be very consistent. My convergence will be faster. So when I am doing this, basically, if I will plot a simple space here, what will happen? These were my earlier space, what would it look like? These will try to come into a common place. Okay, here this might converge to a common point where I will have a mu k and sigma k. Okay, so this is what we are trying to do, right? If you have watched the lecture, am I correct?
But in that case, how will distinguish that for a given input that which is because we are trying to distinguishing between based on the mean, right?
No, we are not trying to distinguish based on the mean. We are trying to give input to the network that does not get disturbed a lot by changing the input. We are saying that if I am going to, like in epoch 0, I have given the input 1 and it has changed the weight from W0 to W1. And if I have gone to epoch 1, and this is the input 2. When W1 to W2 is going, this change from W1 to W2 should be plus minus epsilon. Okay, and this epsilon should be very small. Or you can say that the distribution of W1, you can say the distribution, I'm not sure what I should write. The distribution of W1 should be equal to the distribution of W2. This is what we want. However, if the input is changing and the distribution is changing, then our training is not going to be stable. That's why we want the input to be statistically constant. Or I mean almost constant, not constant. Like it can never happen because the inputs are different, right?
Yes.
So this is what we are doing. So it doesn't matter
Okay.
what kind of transformation we are doing into the input. If the transformation is consistent, it is going to help us in the training. Okay.
So what I understood is based on the normalization, you are trying to bring it to the same common space, correct?
Yes.
Okay, then clear. Yes.
And this is happening to the input. Currently, I am talking about the input, not the
Input.
I mean the input into the hidden layers or into the network. We can discuss in the similar manner there as well, but
Yes.
we understood overall idea, right?
Right.
The,
So are you assuming that everything is normally distributed?
yeah, I mean, if you are sampling something and if you, like, let's say you have 100 data of car and you have 100 data of uh, you say something other, some rows, and if you will plot it, you will get some distribution, and then you can find the mu and sigma,
Yeah.
right?
Yes.
Like it will create a cluster.
Yeah. Whatever be the distribution, you can find mu and sigma.
Yes. Okay.
Right.
So, I mean, normal distribution, it's generally, I mean, uh, if you have the data which are around a mean and you have some sigma, you can call it normal distribution, right?
Yes.
I mean, with
Okay.
with the quantity mu and sigma,
Yeah.
right? You have to specify this. And
Yeah,
if you are saying that if I have normalized this, my in whatever the data I had with this mu and sigma, the my new mu and new sigma will become 1, 0, right?
Yes.
Yeah.
Yes.
Sorry, 0, 1 mu and sigma.
Mean is 0. Yeah.
Yeah.
Sigma is 1.
Yeah. Okay. So we have understood why we are trying to do this, because we want our training to be consistent and stable and not dependent on the input. So, and we have, okay. So now let's talk how we are going to do this. So we are going to talk about the technique that is called batch normalization. So the batch normalization means, let's say if you are training a simple CNN network in which you are giving input of 32 cross 3. Let's say you have a, okay, sorry, 32 cross 32 cross 3, and then you are doing all sub kind of convolution layers, and then max pool, and then similarly it is getting repeated, right? However, this is a one input. But when we talk about the batch normalization, we say we have a certain number of input once it is going inside the network, right? So let's say if in my batch I have 5 inputs. In that case, my input dimension will be 5 cross 32 cross 32 cross 3, right? And if I am using a convolution layer, this is a convolution layer with let's say k number of kernels, then my outputs, and let's say I am assuming that after convolution, my dimension is remaining same of these features. In that case, just a minute. Yeah. In that case, my output should be of dimension of 32 cross 32 cross k. Correct? Okay. So basically, for each kernel, for each input, I will have a simple space, 2D space in which I can call this as I have a k number of kernels here and n number of inputs here, right? Here n is 5 here. Let's call it k is 16. In this case, 16 kernels and 5 inputs. Correct? So after this, I have this much number of data. So for each input, if I have passed the input of 32 cross 32 cross 3, and if I have a k number of kernels for this input, I will get this. I will get this kind of output, right? This one is the output of the first kernel. This is the output of second kernel, third kernel. Similarly, all the 16th kernel for first input. Similarly, for the second input, I will get just I will draw faster. Second input, right? And then these are the k. Let's call it k, and it has also dimension of 32 cross 32 cross k. So similarly, if I have a n number of, then this is the nth out input, right? Now we into the batch normalization, we are saying that from the first kernel, I have got this feature for the first input. For the first kernel, again, I have got this feature for the second input. So, yeah. Okay. So, for the batch normalization, what I will do, I will create the mu and sigma for all the k, for all the output I have got from the kernels from all the n number of inputs I have, right? So basically,
Yes.
here mu k will look like sum of, and let's say this 32 cross 32. Let me write as a w cross b.
Yeah, one
Okay.
thing, can you clarify how it is 32 into 32 into k? I mean, each time k is applied, you are getting 32 into 32 into 1. Kernel.
Yes.
Yes. K is the number of kernel, right? And image size is 32 cross 32. So if k number of properties we are extracting from that 32 cross 32 by various filters, then overall number of processing is 32 cross k, correct?
Okay.
Yes.
So k number of properties we are extracting
Yes.
from 32 into 32.
Yes.
Yes.
Okay. And the 3, what happens to that 3? 32 into 32 into 3 is there, right?
So 3 is the RGB value.
That is RGB, right?
RGB. Okay. Colors.
Yeah.
धीरे धीरे का धीरे का
Okay.
धीरे
कोई
कोरे
नहीं, yeah.
हाँ
Just a minute.
okay wait थोड़ी देर बेरा
Yeah. Okay. So basically, if I am calculating this mu, I will do this 1 by n of W cross B, right? Yeah. For all this dimension, for all the number of inputs, I will be doing the summation over this input, right?
So n is number of input images, or right,
Yes.
which you said 1000, and W into B is 32 cross number of kernel, correct?
Yes. In this case,
Okay.
yeah, n number
In
of
this
input.
case, yes.
I was talking about the 5. So yeah, I was
But
discussing.
you
Yeah.
said batch is
Yeah.
different, right? Input is different, right?
No, like in one training epoch, I am passing 5 inputs.
So input is nothing but 5 images
Yes.
at a time, right?
Yes.
So 1000 we have broken into a batch of 5 into 200 such batches, correct?
Yes.
Okay.
Yes.
Okay, clear.
Got it. Yes. Otherwise, that will not be a batch training, right? And every time the
Then
mu
it's
and the
just
sigma,
stochastic, yes, training.
yeah, every time and mu and sigma will be same only. So we do not have to care about this covariance shift in that case, right? If we are passing all thousands
You're
inputs
right.
at a time.
Yeah.
Yeah. So this is what we will get, and let's call this some value A. This is the A inside this. Like this A is a pixel value for I equal to 1 to n, or W is equal to 1 to W, and B is equal to 1 to B, summation of A of IWB, right? For this kernel K, this is constant, right? And this K will change, so I am trying to find the value of mu K, right? Got it? Similarly, I can calculate.
2 times you wrote W, that is 32 and 32. That's because of both are
Oh,
same, right?
sorry, this is
B.
right. Correct? No issues.
Yeah,
Yeah.
perfect. Yes.
Yeah. So this is how I will calculate this mu K, right? Similarly, I will calculate the sigma K, and I will write 1 by n of W dot B. Okay. So if I am calculating this mu and sigma, and then I can normalize these inputs, like whatever the kernel outputs I have got, what I can write for x, what I want, any notation? I have no. So x, basically xi is equal to mu k, for all xik is equal to mu k minus xik by sigma k, right? For each kernel, right? For each input and each kernel. And then after, since you have got this, you got this normalized value of input for the each kernel. However, this mu and sigma will change in each epoch, right? So you want to say that currently the problem we were trying to solve, it has not been solved, because even though we are changing, we are normalizing this mu and sigma is different in each epoch, and hence this space will be shifting each time, right? And then we are saying that, okay, I have created the space of mu sigma, and let's bring back this mu sigma to a point. Okay. And in that case, I will write the xyik as equal to gamma into xik plus beta. And we are saying that we don't know the value of gamma and beta. So basically, these are the trainable quantity. These are the parameters. Any problem? Yeah.
So gamma and beta are such that for the same gamma and beta value for all the batch, we get the
Yes.
same mu and k, mu and sigma, correct?
This mu and sigma.
Yeah. No, but
No,
this
these and
mu
mu
and
and sigma.
sigma for all 5 batch, we are getting the same mu and k value for us particular gamma and beta, correct?
Yes, yes.
Yes.
So basically, let's assume this mu and sigma. Let's assume this mu as a one quantity. This mu will be another quantity. This mu will be another quantity. Something like this. And basically, you can create a overall mu that is basically in this case gamma. Are you able to imagine?
Average of all mu's, yes.
Yes, exactly. In some sense,
Mean of all mu's, yeah.
yes, yes. And whatever the mean of all, and then there will be variance of all those mu, that will be beta. Okay.
Okay.
I mean, I think it should be imaginable, right? So
Yeah,
in
yeah,
that
okay.
case, so basically now we have converted the input to a one value. Like even though if we would have given the 1,000 inputs at a time, in that case, whatever the mu and sigma we would have gotten, that would be approximately equal to gamma and beta. Would it should be. I
Yeah,
mean, you should
yeah.
test it. Sometimes try to test it in your write your code and okay. Even though we are saying that trainable quantity, even though if we will not train it, it it should be become better. But since we are doing this training, in the training is in process, if we will directly give the value of gamma and beta here, there might be a chance of convergence because we want this to change slowly over all the training process, at least in one batch. I mean, in one go. In like one go means all the 200 batch has been trained once. Again, this is changing. Like let's say you have given the original value of gamma and beta, assuming that you have tried to find the value of mu and sigma. Yeah, there is another thing as well. At the input, we only know this gamma and beta, right? But currently we are talking about the kernels, and kernel is transforming the input, right? In that case, we don't know the value of gamma and beta. Got it? Yeah, I was just confused, so I cleared myself.
So see, this gamma and beta is different for each kernel, correct?
Yes.
Yeah.
Yeah. Like let's say if you have an input, only input, and you are trying to find the batch mu and sigma for the input, and then you are trying to get the value of gamma and beta, and try to find the value of mu and sigma for all 1,001s. That gamma beta should be equal to this mu and sigma, just for the intuition, right? Because these are the simple data that is not changing over the time. Got it?
Yeah.
Yeah. However, we are talking about the kernel in that sense that is getting trained, that is changing every time. So basically, this gamma and beta will be changing, but we want that to be converged to some value, and maybe like the change of gamma should be very smaller and get converged to a value. And in that case, we will say that my input has or the feature is normalized to one value of gamma and beta, right? Okay. So this is what we can do in the input. However, let's talk a little bit about a simple MLP, multi-layer perceptron, in which I have a layer L minus 1. I have another layer of L plus 1. So basically, you can write the output of this network as AL, right? You can write the output of this network as AL plus 1. And the output is AL plus 2. Right. So basically, when you are saying the output AL, actually AL is actually function of uh, W and like you can write WL minus 1 and AL minus 1, right?
Yes.
Correct?
Yes.
Yeah. So now here we are trying to say that we will train the network such that the this distribution of AL should be also normal, and the value of mu and sigma for AL should not change over the batches. Okay, or we are or for this as well, or this as well, this as well, or this as well. Right. So either you can normalize the output or you can normalize this weight. You can go for either of them. Anything is fine, because we are talking about the quantity that is going to change our output, because this function is not doing anything. I mean, this function is not participating in the stochasticity of the data. This is just a function that is going to produce output. So either we can normalize this or we can normalize this. Anything is fine, right?
So normalizing means converting into Z coordinates. There's x minus mu by Z, x minus mu by sigma.
Yeah, yes. So let's see, if you'll discuss a perceptron, and if the input is AL minus 1, what you do, you have a sigma here that contains, and then you get the output F that you call AL. Sorry. Yeah. This is AL, right? This sigma is basically WL minus 1 into AL minus 1, right? And once you get here, basically WL minus 1 into AL minus 1. So what I'm trying to say, that normalizing this process before reaching this, what you will do, you will go through an extra process in between, that you will say batch normalization, and then you will do the F.
Inside each neuron.
Yeah, after this calculation, inside each layer. Okay. So when you are doing this batch normalization, basically you are trying to create an independent space for this layer from this layer L plus 1 or layer L minus 1.
But sorry,
Because
each layer is formed by multiple perceptrons, right?
yes.
So that means multiple means array of neurons. So in each array of neurons, each neuron we are inserting one more layer, correct?
Yeah,
Or no?
like let's say this neuron is taking n number of inputs. Okay. So it will have n number of W, right?
Yes.
And if it's creating like m number of output, then here you will have a m number of weights again that will go inside here, right?
Yes.
So if this is taking if this neuron is taking W in number of weights, then this weights will create a distribution, right? It will create a histogram. Like let's say this value of 0.1, another will have a value of minus 0.1 or something minus 0.2. So this will create a histogram, right?
Right.
Like this.
Understood.
And this histogram will have this mu and this sigma, right? And we want to say that for each neuron, whatever the mu and sigma will be there, it should not change after batch normalization. Like we are training over it. So this batch normalization act in a way that this should stop changing over the epoch. Got it?
Yeah, clear. Yes.
Yes. Yeah. So this is what the batch normalization look like. Okay, just a minute. Okay. But what is the problem with the batch normalization? Batch normalization always takes certain number of input to create the value of mu and sigma, right? When you are testing or you are validating, you don't give that much number of input at a time. You will give one input and you will say whatever you wanted to predict, are you getting that or not, right? In that case, what kind of mu and sigma you will use for the prediction? Like let's say you have trained your network and then you want to do the validation or you are doing the validation in between. However, you are not giving all 5 number of inputs. You are giving one input only at a time, right? So basically, you will save these parameters gamma and beta, mu and sigma, and then for that gamma, beta, and mu sigma, if you will give the input, you will find the validation losses, okay, or the test losses. There is a problem here again. If you are giving the one input, even your gamma and beta will be constant.
Voice, please. Not able to hear anything, sir.
We cannot hear you.
Unable to hear you.
You're able to hear? Yeah.
Oh, now yes.
Okay, I have removed the
Yeah. Now better. Yes.
Now
Okay.
better.
Thanks. Yeah.
Just give me. Okay. So it is better, right? Okay. So I was telling, yes. So if I will give my input, I don't know the value of mu and sigma. Although I know the gamma and beta, that is not going to change. That is why we were training this to get this constant value of gamma beta for the kernel layers. But mu and sigma, that is going to change for the inputs every time. So we don't know that value. So what we will do? We will give the first input. We will record this value of gamma or beta. We will give the second input. We will update the gamma and beta, not mu and sigma. And we will do three. We will keep giving the input 3 for input, and then I will take the average of mu and sigma, and then I can be dependent on this mu and sigma. However, this will never change, and then I will have a better validation. Okay. Who is there now? Okay. Second problem, when we are doing this batch normalization, basically this batch normalization is a kind of serial task. What does it mean by serial task? Like you have a, let's say you have a n number of inputs in the batch. You are basically dependent on all the n number to get the mu and sigma. Right. So every time when you are doing this mu and sigma, your computational cost is increasing and you are waiting for all of them, and hence this process is slow. Okay. Again, when you are doing some kind of a recurrent neural network, little bit of idea about recurrent neural network is that recurrent neural network generally takes the time dependent problem. So let's say if I am giving one input, I have trained my neural network, I have got my output, then like it's I equal to I, and then it's I equal to I plus 1. That means this output is always dependent on this input, right? So you cannot give like a 5 input and then you predict the 5 input. This will never happen. You will give the one input, you will predict the second output. If you give the third input, you will predict the fourth output. So this is always a serial process, and this is always a sequence is there. And when there is a sequence, you cannot do things in parallel, right? So that's why you cannot do the batch normalization into the recurrent neural network. Any doubt about the recurrent? I'm sure I have not explained better. Let me do it again. Like let's say when you solve any time dependent problem, let's say dou u by dou t plus f of uh, x comma t is equal to 0. And when you solve this equation, you always say that, let me write this. When you solve this equation, you say that ui plus 1 is equal to ui plus dt into f of x comma t comma u. Okay. So you say that if you want to calculate the ui plus 1, you need the ui, right? Let's write ui. If you don't know the ui, you cannot calculate the ui plus 1. So this is a kind of forward process, right? Time always moves in the forward, right? You cannot go back into the time. So similarly, this recurrent neural network solves the time dependent problem, and it always goes into the forward process. So my second output is dependent on my first input. My fourth output is dependent on my third input. My third output is dependent on my second input. So there's a dependency, linear dependency. So you cannot say that, okay, I will give my 5 input and I will predict the 5 input. But like in this case, you can call it like there are the system in which you can do that. Like let's say you are in this neural network, you are predicting two quantities and those quantities are independent of each other, then you can do both of them parallelly. Like let's say you are solving for let's say you are doing a weather prediction, and at day 1, temperature at day 1, You are giving the input and you are predicting the temperature at day 2. Okay. Let's take the another independent quantity that this weather prediction model is using, and let's call what you can call. Well, weather prediction model is very complicated. I mean, any independent example that I should take. I mean, what should I say?
1 second.
Yeah, let's say the rain.
Rain
Let's say,
on a particular day. Yeah.
yeah, like number of
In a rainy season, or number of rains in a previous year and this year. Number of rains.
yeah, I mean,
Anything.
I mean, let's say every temperature in per day, and not year. Let's say rain at day 1 and day 2. Okay, like it goes into a quantity of the inch number, the amount of inch it has rained day 1. It is dependent on date. The day 2 will be dependent on day 1, something like this. But these are quite related. Like weather is way too complicated. But let's assume that both are not related. Then you can give these two quantities as input and you can predict these quantities, right? However, if you are training for this temperature or you're training for the amount of inch water has rained each day, and like let's say you are predicting for day 3 and day 3 and for the day 6 simultaneously, you cannot do that because day 6 is always going to be dependent on day 3, right? So in that case, this linear dependency will not help you into this batch normalization. You can always give one input at a time. Okay. So now we are going to discuss a little bit about the group normalization. Since we have understood this batch normalization, understanding the group normalization is very easy. So what we are saying in this group normalization, I have an input of 32 cross 32 cross 3. I will create from the K kernel, my output has become 32 cross 32 cross K. And then I am taking the mean over these K values. Or like in this case, my mu will become 1 by K of W cross B of A of K equal to 1 to K, W is equal to 1 to W. Okay. And this N is basically now my independent quantity. So if N number of inputs I am getting, I can calculate the value of mu N. I mean, the mu will be independent for the different respective inputs, right? Previously, we were taking, like if I had the first kernel, I was taking the mu for all the inputs. I was taking the mu K, right? However, I am to find for each input, I am trying to find the mu N, in which I am trying to take the average over all the kernels, right? So this is called the group normalization, and in each case, I will pass an input. I will get a different mu N for over all this K, right? So this is a simple concept of mu, the group normalization. So how it is different, that is the point of discussion now. So what happens when you try to do any kind of training, and let's say this is a graph, this is the epoch, and this is the loss, or you can call it error. Let's call it error for right now. And if you are doing this batch normalization, then what will happen? this convergence will depend on number of what is the size of your batch. Like let's say if you are training for the batch size of 10, 20, 30, let's write 1, 2, 4, 8, and 16. Okay. So in the case of batch normalization, the more your batch is, the better the convergence you will get. Okay. So if this is my convergence for batch size of 8, then this will be my for the batch size of 1. And this will be my convergence for batch size of 16. Well, if I am getting a better convergence, then why not all the data is input? You cannot do that, right? That's we are trying to solve for all the input because you have the whatever the computational facility you are using that has the limitation, the number of memory, the number of RAM it has, the number of uh, the cache it has. So you want to do create a batch. Also, let's say if you are using the batch size of 16, you are getting some convergence. Let's say you have used the batch size of 32 and you are getting a similar convergence. However, you are saying that you need a bigger GPU to do that. Then you are fine with the batch size of 16, right? However, in the case of a group normalization, whatever the group size you take, your convergence will look same. Always it will look same. So your convergence is independent of your number of groups you are creating at the input. Okay. So which is better? Obviously, in some case the batch is better, the some case the group normalization is better. Okay. But there is a problem with the batch that you have a hyperparameter here. Right. And generally the batch normalization and group normalization at the most efficient number of batch, they almost converge in the similar way. So basically you can go with the group normalization without caring about the number of batch you are calculating. At least into the case of CNN and MLP as well. Okay. Now let's discuss another normalization that is called the instance normalization. Yeah, so one more thing. In the group normalization, let's draw another figure that we were discussing earlier. So this is the n number of input and this is k number of a kernel. So this is my kernel 1, kernel 2, kernel 3. This is my first input, second input, third input, fourth input. So into the batch normalization, I was averaging over this for each kernel. But into the group normalization, I was averaging over the each input to find the value of mu and k, sigma, just to make the concept better. Okay.
Could you please repeat the last one? These two, vertical and horizontal one. The horizontal is batch, right?
The horizontal is the number of inputs in my batch. This one, these are the columns, and these are the kernels I am using for each input.
Okay.
And
so when we are taking the averaging on kernel, that is batch, right?
Yes.
Okay.
And if I am taking the averaging on each input for all the kernel, that is a group normalization.
Group normal. Okay. Thanks.
Okay. Right. Yeah.
Yeah, thanks.
And the instance normalization is basically the concept where I will find the mu and sigma for each kernel and each group. So I will find the sigma here, I will find the sigma here, I will find the sigma here, here. Right. And obviously it looks worse by seeing only that. Let's say you have taken the 5 input and like how much you have? 6 input here. Let's say 6 input here. You have changed the input and again you are trying to find the value for this first kernel. Basically, you are trying to say that my first input is always should have a same kind to get my best result. However, whenever you are creating the batch, you are not saying that my first input should be rows and second input should be something else, right? So basically this is random. Choosing the batch and the inputs is random. So this instance normalization is not any help at all. And this is always going to give you the worst result. Because this is not trying to create any relation with anyone. As you, right?
Yeah, we are not leveraging any correlation.
Yes.
It is individual. Everything is individual.
Yes. And then there is a what is the another name? Group. Yeah, group normalization.
Batch, group, and instance. Yeah.
So what is what? It was group, batch, and there was another one. Forgot the name. Just let me check.
दार उघडा राहिले डास येत आहेत खूप.
Okay. Just give me a minute. Ah.
Is to learning. The basic blockers because this which are design can be faster or the training of the. Hello.
Is it layer optimization?
No.
Batch normalization, layer, instance,
Somewhere
group.
in between the group and the batch and the instance.
It is on layer optimization as well.
No, the layer optimization comes in between. It just
Okay.
like what it happens. Let me explain you.
Yeah.
So you have these kernels. You have these kernels. Okay, forget about the name. We will directly discuss the concept. So like basically when you are creating the kernel, so in the batch normalization, we were saying that I will try to find the mean for each kernel for all the inputs, right? And in the group, we are saying that we will find the mean over all the kernel. However, in the this given normalization, we will say that I will try to normalize for few number of uh, few number of kernel, like something like this, like for all the some number of input. Does that mean that so I have the input first kernel, second kernel, third kernel, fourth kernel. So instead of taking the mean over all the kernel, I will take the mean of two kernel only. Understood? Like, and I will create the mu for two kernel only. So I will not take the mean for all the kernels. So basically they are saying that I know that, like let's say, if you remember the how the k we were calculating, like let's say if we were calculating the 16 kernel from a given input, we were saying that, okay, whatever the input I have, I was creating this permutation combination, right? So I will take the value of k in this way, right? If you
Yes.
remember this,
Yes.
then I will take these 4 values,
Yes.
right? So basically you can say that these number of kernels working into the same way, right?
But if
These
we
number,
see, these kernels are doing different job. Like for example, for one image, one kernel may be doing say uh, orientation in the horizontal direction. One kernel may be calculating orientation in the vertical dimension, vertical direction, right? So if we are grouping them together, then
yeah,
is it
wait,
not going to?
wait. So when I am saying that I have already some kernels, and from that kernel I have got the output, and then I am creating another kernel. There I am saying that if I am taking the combination of 3, then I am trying to create a something called, let's say, some curve something like this. But when I am trying to create the combination of 4, maybe my combinations are something like this. So basically the something that looks something like this or like this or like this, I can take these kind of the features together, and then I can do normalize. If I am getting something like this feature or like this feature, then I mean, right, understood, right? So if I am getting these kind of features from the kernel, I can do the normalization over this. Got my point?
Okay. Yeah. Okay.
What is the name of this method you said? Sorry.
This one.
No, this kind of normalization.
No, I am saying
Sorry?
that, yeah, just wait. Let me tell you the name, otherwise this is going to be mess.
Welcome back to the NPTEL online certification of the category.
Oh, sorry. Yeah, yeah, I had this. Yeah. So this was the batch normalization. This is called the layer normalization. The group is basically, this is called layer normalization. So working on all the layers from the kernel. Okay. This is the instance normalization. And what we are discussing now, that is called the group normalization. Okay.
Okay, grouping number of kernels, correct? Yeah.
Yes, grouping number of kernels.
Okay.
So what we discussed, this is this is uh, this is the layer normalization. This is the batch
Horizontal is
normalization.
batch normalization.
And then we talked about the instance, and this is the group one. This is the group normalization.
So probably they're named layer because we are talking about multiple layers, all the K kernels, right?
Yes.
At
Yeah.
once, correct?
Yeah.
Isn't it?
Maybe we should have called it the kernel normalization. That would have better.
Yeah, but kernel is synonymous to layer. Yeah.
Yeah. But you can, okay, right, because calling layer is a more general because you don't use kernel into the MLP, right? Yeah, great. Yeah,
Yes.
yeah, okay. So you got it, right?
Yeah.
So instance normalization will involve less number of subset of kernels. Right.
Instance
One at a time.
normalization,
One at a time, right?
one at a time.
Only
One
one
at a
kernel.
time.
Only one at a time.
Hmm.
Okay. But what you told now, that is actually the group normalization.
If you take
So
all of
from
them
these
together,
you are
all
taking,
of them,
and then you are taking the mean.
all of them together you take, you call it group. Right?
No,
Group
all of
normalization.
when we take all of them and then we find the value of mu for all the kernels, that is called layer normalization.
Mhm.
Yeah. Okay, so now we talked about this different kind of normalization, and so let's discuss a little bit about the training. So when we talk about the training, we discuss about this uh, validation loss and test loss, right? Then we talk about the overfitting and overfitting and underfitting. And the third is that speed of convergence. So the third one we discussed like this batch normalization or any kind of, generally the normalization helps in increasing the convergence, right? Like you can get these loss smaller into the fewer epoch compared to without normalization. And then there is a discussion like which normalization is better, right? Now there is another discussion that is called how much weight is better. Is the weight that we are training is overfitting or underfitting, right? So when we say that when that overfitting is happening, in that case, my test, the validation loss is basically increasing after some time. However, my training is basically decreasing. So what is happening? So when you have a data, let's say this is some kind of pattern you are training. And ideally your output should look something like this. But when you trained and this is what your prediction looks like, then you
So
say that.
y-axis loss you are putting, right? Or error.
Yeah, loss epoch. Okay. And these are the features. Let's call it Z1 and Z2 or X and Y. Let's call it X and Y. These are the input output relation that you are trying to train it. Let's say you are doing a regression, nonlinear regression. Okay. So this is what your output is after the training. Then you are saying that ideally your features that neural network should predict should look like this. However, this looks very linear. So this is called underfitting. So in that case, your loss will look like this, and even this is like training loss, or even your test loss will be also of similar order. Basically, you are saying that the convergence is not happening. So even test loss and the training loss both are higher. Okay. But if you are training such that your predict whatever you have trained and it looks okay, sorry, it looks something like this, then you are saying that you have overfitted. And in that case, your loss will look something like this. This is epoch. Your loss will go down. However, this will be your training loss, validation loss or test loss. Let's call it test loss, validation loss. This is your training. So what is happening? you are unnecessarily fitting the data. Fitting the data means whatever the input you are giving, input output you are training for, that is exactly matching the value. Like you had the input here for the training, you had the input here for the training, you had the input here for the training, and you exactly got the value you were training for. So what happened when you are testing somewhere here, let's say somewhere here, ideally your output should come here, but you are predicting here. So this is your error, right? If you are predicting here, ideally your output should be here, but you are predicting here. So this is your error. And in that case, your error will be higher. This is your error. And however, when you are predicting here, here, your loss is very, very small. So this is called overfitting. To even though, like, let's say if your test loss is not going down or the training loss is not going down, either you can increase number of the parameter, increase number of parameter, because if your data is complex, like let's say your data is trying to predict something called ax square plus bx plus c, but the number of weights you have given that can only predict wx plus b or bx ax plus b, then this a and b will never predict this, right? Got it? So this will always underfit. In that case, at least you need 3 parameter, and your input, like if your x is input, you can create a feature of x square and you can give that x square as input. And if you are creating a, b, c, at least 3 number as a parameter, then only you can train this parabola. However, if you are giving a and b as a parameter and you are giving like, okay, I want to train the a and b, however, my data says that my relation is parabolic, then this linear relation will never train the parabola, right? And in that case, you need to increase the number of parameters, something like cx square, or just create some nonlinearity using neural network, and that will train the cx square, right? So that is about the underfitting. However, overfitting is like, okay, you don't want to compromise, so instead of 4 parameter, you have introduced 10 parameters. Instead of 4, you introduced 10 parameters. And what is the 10 parameter is doing? It is overfitting. When the overfitting was happening, what we were doing? We were adding the regularization. We were saying that, okay, if this is my loss, I will add the lambda for W square. Remember? And we will say that this lambda is a small number, let's say 0.8.
Regularization.
Yeah, this is the regularizer, and this is called regularization, right? And we will say that, okay, this value should be small enough so that the overfitting should not happen. I mean, the W should not become 1 such that it should copy the value, right? Like let's say you have a matrix of 2 by 2 that in which you are having W1, W2, W3, and W4. You are trying to find the relation of AB is equal to CD. And we are saying that even W1 and W3 is enough. However, you have extra W2 and W4. In that case, this will try to become 1 because they are not trying to contribute it. But you want to say that I don't want it to be maximum, I want it to be minimum. If it's trying to become 0, be it. I don't care. But I want it to be minimum. And if this is becoming minimum, that means this is there or not there, it is not helping. I mean, we don't care, right? if we are adding the regularization, this will become 0. And in that case, whatever we needed W1 and W3, it is doing our work. Okay. So that's why we need the regularization. Also, so when we were talking about this batch normalization, we were saying that when we are adding the batch normalization into the layer, basically we are trying to separate the relation of layer 1 with layer 0 or layer 2 with layer 1. Because once we are doing the normalization, we are changing the value, and in that way, the direct relation, we are breaking the direct relation, right? Like, even though there is a, like, since we are having the neural network, the graph is available there, but this value of mu and sigma over each neuron is breaking a direct relation. A direct relation in the sense that if my input is looking like this, and if my output is something like, let's say this is ax plus b, and if I am multiplying with w of ax plus b, this is pretty straightforward because I want my output to look something like this, let's say, because w has been multiplied and some weight has been compromised, right? And hence this is my output. However, we will say that instead of ax plus b, we will say that I will multiply with some mu plus b that is not directly dependent on this mu. So basically, this kind of shift is happening as well, instead of only the multiplication. And this shift is creating a breakage between the relations. Got it? I mean, try to imagine it like this shift is creating a problem. This is trying to break a direct relation in some way. Okay. I mean, what is the term you are using while explaining or understanding the concept? That is important. And when you are trying to break the relation, then each neural network has to train independently in a way that they will. Yeah. Are you getting the noise of outside, or you are fine with it?
No noise.
Okay. Okay. So I am getting some noise. Okay. Okay. Yes. So yeah, this is disturbing. Let me use my headphone. Hello. Am I audible?
Yes.
Okay. Thank you. Yeah. Yes. So once we are creating this mu and sigma, we are saying that this normalization will itself try to train those layers independently, and in that case, this batch normalization will itself act as some kind of regularizer. Okay. And what about the other concept? Yes. Okay. And then there was another concept of dropout. I think we have already discussed the dropout earlier, in which if I will have an input layer and then I will have an output layer, and if I will say that in layer L at each epoch that 50% of my neuron should switch off. Okay, that means if I am switching off the 50% of the neuron, so randomly I am picking these two neurons and they are not going to take part into the training at current epoch. Then what will happen? This this will only change the weight that has a direct relation with this one, 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 and this one. And whatever the relation this has with this one, the weight that will not be either used for the output or used for the training. Okay. And in that way, I will say that I am trying to use the lesser number of neurons to create a better relation between input and output. And in that way, this neurons has to force them to train, even though I am using a higher number of neurons, because these are not getting used as a part of training in the current epoch. In the next epoch, maybe this will not get used and this will not get used, and these two are getting used. But my idea of writing the algorithm is that random certain percentage of that neuron from that layer will not participate in the training as well as creating the output. Okay. So this is what the simple concept of dropout is. And that dropout will also act as a regularizer. And that regularizer will not overfit the solution. Right.
So the dropout is chosen based on random, right?
Yes.
Random. So each time you run, you will get different results.
But
Will you get different results each time you run because you are choosing one random basis, or you will get consistent results?
no, we have output here. This is some hidden layer. I was not talking about this as the output layer. This is some hidden layer. So we
what
should
I'm
get
saying, final output.
Yes.
Yeah. Consistent you will get, or based on because you are chosen on random basis if in each layer dropping. So we'll get different outputs. So during each run.
No, we will get the consistent output because the idea is that we should not train the each weights a lot such that the overfitting should happen. Like let's say sometime this net in this, if these two are not getting trained, then this will remain constant. Next, if it might get trained once. So there's some changes there, and we are always going to create the loss DL by DW, right? Whatever the W available has not been frozen in that case. So whenever that will get trained, that is going to participate in the loss, and that will make this loss smaller, and that will be always constant, consistent, right?
I think the easier way to say visualize this is, for example, in a team of cricket, 11 players are there. Okay. So we are not relying on a one particular person. So if we say three persons are not playing well, then weight will come on rest of the 8, correct? And still they are able to win. So now these 3 or 4, any 4 can be underperforming at a certain time, but team is still winning. Maybe easier way. We are not relying on Sachin Tendulkar. So weight on each weight is fitted such a way that irrespective of who is contributing, but still team is still winning, or here the error or loss is the minimum.
Yeah. So I will extend little bit your explanation. Like let's say the team is playing a tournament, and basically each game in the tournament is basically a epoch. And then some number of players not performed in this in this match, but they performed better in the next match because
Perfect.
they have tried. Got it? Yeah. Thank you. Yeah. And
But
what about
the analogy? Which 3 will be dropped will be based on, if you drop based on random, those who are playing well also may be dropped. No, those who play
exactly.
well.
Yeah, exactly.
And those who do not play well also may get included because you are doing on the random basis.
Random basis. So in such a way that the neural network is designed in such a way that even if it is not relying on a particular node at all, even if you drop that node, the output will be consistent.
output will be same
Yes,
Consistent. Yes. Yes.
consistent.
because all nodes are equivalent role they are playing.
Exactly.
There is nothing like one node is more important, another node is less important.
Exactly. No, there is no under or over.
So that is why cricket analogy will not apply here.
See, let's extend a little bit because you told like that. So even let's say you made a team, you have been given a role of a captain. You are not aware that how the people are doing, but you have been given a team as a captain, and you start training them over the tournament. And after some time, you will train them such a way that everyone will perform, even though everyone will know how to perform, even though someone is having a bad day. You are going to win it.
Got it. Yes. Yes.
I think this should be the best
Yeah, they will
explanation.
average out. Average
Yes.
out. Overall, it will average out.
Yes. Yeah. Yeah. Got it.
Yes.
Yeah. This is interesting. Oh, okay. I think we don't have anything else in this week. I guess. Let me check. Okay. So let's solve some question and then.
Yeah, that is how organizations function. See, all will not perform in the same way, but they
Yes.
complement each other. Complement each other in different ways, and organization output will be there. See,
Yes. Yes.
not everyone will work in the same way.
Right. Right. But as a captain, you should be good enough to know how to use your team and how to train everyone or certain times to perform whenever someone is not there, right? Yeah.
Correct, correct. So neural network is working like that. Okay.
Yeah.
So
I mean,
training.
why not? Yeah. Are you able to see the screen, right?
Yes.
Let me go there. Okay. So yeah, what is a not a reason for using the batch normalization?
What is inference time?
Inference is prediction.
Then D should be the answer. Covariant shift.
No, option C should be correct, right? We want we are using the batch normalization so that we can prevent the covariant shift. Like prevent means we don't want the variance should to change every epoch, right?
We want it, yeah. But
So
it will
yeah,
converge faster, right? Okay, that
yeah,
is B.
yeah. So not region. So what is not the region of using? Like I talked about the inferencing. Like when you are using the prediction, when you will give the first input, you will calculate the mu and sigma. When you will give the second input, you will calculate the mu and sigma, and then you will take the weighted average of those mu and sigma. And after few weighted average, you will be able to get the correct value prediction, right? So I think option C should
C.
be the correct. Yeah. The neural network has three neurons in the middle layer. Activations of neurons of three batches are respectively. What will be the value of mean if you use the batch normalization in this layer?
Mean of batch. 7 by 3. 4.33 and 9 billion 13 4.33. I think so. A.
Yeah, option A should be the correct one, right?
3.33. Yeah, yeah. Sigma of each value divided by 3.
Yes. If it would have been a layer normalization, you would have averaged over this, right?
3 plus 2 plus 1 divided by 3. Yeah.
Yes. Correct. Correct. Okay. How can we prevent underfitting? We discussed just now.
Number of features, increase number of features.
Correct.
B.
How do we generally calculate mean and variance during testing?
During testing, it is required mean and variance based on test image. Estimated mean and variance statistics during training. Estimated mean, that means E. Or predicted
Often,
value cap. Once again. C.
yeah, like we used it, right?
The
Yeah.
hat, right? Hat. S.
Yeah.
Y cap or something.
Yes, yes. No,
Yeah,
like
okay.
the gamma and beta that we calculate, we use that. Like let's say we are using
Okay.
the group normalization and I mean the layer normalization. Then you will simply use this gamma and beta, right?
Ground. Okay. Could we see the solution of the scroll up, please? We generally calculate the batch mean and variance statistics during the training and use the estimated batch mean. The mean of all mean and mean of all variance. That's what you said, gamma
Yeah.
and beta, correct? Yeah.
Yeah, like when you are talking about the mu and sigma, you will have to calculate from the test image. However, when you are talking about gamma and beta, that you will use from the training.
Correct.
Which of the following is not the advantage of dropout?
Accuracy. D is definitely required. So improving accuracy is also needed. Prevent overfitting.
No, this is testing. Don't underlook this one testing.
Reduce computation cost during testing.
When we do the testing,
Yeah, that is not the.
we activate all the neurons. And dropout doesn't care about the testing. It's dropout is a part of training, right?
Really, yes.
Yeah,
So
correct.
D.
Yeah, D is the answer.
Yes.
What is the minimum? Layer. C.
Option C should be correct, right?
Recurrent
Yes.
neural network RNN. Because you are saying that it is function
Yes,
of
I
time,
mean,
right? Yeah.
yeah, we cannot use multiple input at a time. And, and what is like, we need the one input and multiple features of it for the layer normalization, right? So we can directly use it in the RNN.
That means for one image, all the kernels we can use at a time. We don't have
Yes.
to wait for the second image to process through the
Yes.
same kernel.
Yes, because we are trying to find the mu and sigma over all the kernels for that
Yes.
input.
For that input, yes. Training of a neural.
Oh, I did not discuss it, but yeah, you should.
Training and validation. Which is best for early stopping, okay?
So name itself suggests what the early stopping means. Like when you want to stop the training. Got it? Tell
Once
A, B,
again.
C.
At which layer you want to say, correct?
At which time?
Time,
Like A, B.
yeah.
When you want to stop that trend.
Validation and train.
C,
Training is becoming almost,
C, right? After C, it is increasing validation error.
no, but
Yes,
that is validation, okay?
Up to C, it is decreasing.
correct. Correct.
So,
I mean,
yeah,
then
After C,
after
more difference will be there
after C,
between
it is
training and validation.
Yeah.
overfitting.
Yeah,
After C.
correct. Yeah. After C, the overfitting is happening. So at C, you have to stop it.
Mm.
So basically, you will, when you write the code, you will create like if else, or you will create a condition where you will say that if my validation loss is increasing, stop here. That is called early stopping. Like
But
you like let's say you are training for 100 or 200 epoch, but after 50 epoch only your validation loss is started increasing. Even though your training loss is decreasing, you will say that okay, I don't want to train for 200. 50 is good enough for me. That is called early stopping. Yeah,
but
go on.
validation means we are giving a unknown vector, right? Input, unknown
Yes,
image.
yeah, like you have some number of input. You have randomly you have chosen some value from the overall data set, and you have placed them for the validation.
Yeah, which were not used in training set, you are using.
Training set we are giving that. So after
Yes.
C, it is that loss is increasing. That means C is a proper way, a proper time to stop the training.
Yes.
Correct?
Yes.
Yeah, okay.
Yes.
But sorry, could you go again back? Yeah, that means training and validation keeps happen simultaneously. Usually.
Yeah, I mean, yes, yes. Like you train it and then you predict it.
Correct.
Okay.
Unseen data. Validation is unseen data during training. That
Exactly. So earlier I was thinking that we say train it first and then at the end we validate with the unknowns.
No,
So
no.
now
So
that
that
should
is
go
called
hand
test.
in hand. Okay.
That is called testing.
Okay.
Like
That is testing.
yeah. So you convert the data into three sets: training,
Okay.
validation, and testing. So validation you use only for checking where you want to stop it. Are you
Okay.
overfitting or underfitting?
So where you want to stop training, you want
Okay.
to use this validation data.
Sometimes people use some testing data set outside of the data you had while you have just you want to see like
Hello.
uh, uh,
మళ్ళీ కాల్ చేయనా ఇక్కడ ఏదో లెక్చర్ జరుగుతుంది కాల్ చేస్తా.
yeah. So sometimes you create a testing data set outside of your overall data set to check if the are you able to extrapolate your information from that your network as well. Like that is a extra study. Like people generally don't do that because we generally assume that neural network cannot extrapolate the information. Like let's say you have training from 0 to 1 and you are trying to predict for 1.2, you are going to get an error. So, but you can test sometime like how much error you are getting, like how much you can extrapolate. So those kind of things.
Now this training, validation and testing, generally how much percentage split will be there?
60, 20, 20, something like this, or 70, 70, 20, 10, something like this.
Okay, okay.
Sorry, I have one more question here. I am taking
Yeah,
more
yeah.
time. Sorry
Yeah,
about
it's
that.
fine.
Suppose training validation happened well, and suppose we stopped at point C here, but if when we gave the testing, right, it failed, suppose, for say a majority of the test cases, say 50%. That means our training has to be redone, correct? Or our input vectors have to be increased again. Does it mean like that?
See, like let's say you have an input, you have one data, you have 100 data set, and
Mhm.
whenever you are separating your training, testing, and validation, you basically you assume that your data is independent and identical. Okay, you know, IID like So they are identical in a way that they are coming from, like if you will try to find the mu and sigma of your training, testing, and validation, they should have a similar value.
Properties, yes.
Yeah.
Mm.
So that is what IID, right? And
Mm.
and in that case, whatever you are telling, that would never happen. That's why the validation is happening. And you are saying that if the validation is correct, if the solution is converging, and if
Mm.
the overfitting is not happening, then at least 70% your prediction should be correct. I mean, it depends upon how you are checking the error. But let's say in the case of validation, your error is 70%, and I mean, your error is 30%, and training your error is 25%. Then even in your testing, the maximum error you will get is around 30% only.
So here,
Okay.
this time axis is same as number of epochs also.
Yes.
Number of
Yes.
epochs.
Yeah. Yeah. Go on. Milind.
Yeah, means
X-axis.
You got that, right?
yeah, I got it, but maybe I can give one example. For example, I'm taking more time. For example, we trained the say flower and car. Okay, now only these two inputs. Now flower always it was a front view and car also front view. So it got trained. Now in the testing, I gave a side view of a car or side view of a flower or rose. It could not make it out that. So that means our trainings data set was not enough.
Yeah. In that case, your mu and sigma of the car you are telling that has the information of side view, but you have trained or validated for
On the
the front view. That means mu and sigma is very different for your testing
Very
data.
different.
Yeah.
That
So
means training has
basically,
to elaborate.
yeah. I mean,
Exactly.
the mu and sigma should be IID, right?
Perfect. Yeah.
So
Clear.
that means
Thank you.
everything you are converting into mu and sigma.
Yeah. I mean, it's easier to analyze. I mean, understand mathematically, right?
Okay, okay. Numbers.
Perfect.
Yeah.
Thank you.
Numbers. Yeah. Statistics are good.
Okay.
Yeah. Which
Very
of
fine.
which among the following is not a data augmentation technique? Random horizontal and vertical flip of image, random shuffle of pixel in an image, random color jittering. Wow. Option C should be incorrect.
Shuffle of pixel color also we don't do that.
What is the meaning of random color jittering?
Not data.
What is the meaning of random color jittering?
I don't know. Let me check.
Jitter means like a
I
flickering.
think D,
Okay.
right?
Flickering.
Degree.
Flickering. Jitter means flicker. Okay.
Flicker.
Yeah. So random color flickering is not a data
It is
augmentation.
not a data
technique.
thing. Yes.
Means we usually do not play around with a RGB of an image. We don't do.
Yeah. A, B, and D are data things. A, B are data things. C is not data things.
But we
Pixel also I
cannot.
have never heard. B also I have
No.
never heard.
I mean, option B should be incorrect in a way that, like, even though let's say you are doing some color jittering, however, you are not playing with the, let's say, edges.
Exactly.
Okay.
That's what I was saying, that I have never heard that we change the places of pixel. So for example,
I mean,
then rose will become something else. Correct? If you
yes,
do
yes,
this.
yes. So option
So
B should be incorrect.
B should be the correct answer.
Yes, yeah, correct. Yeah, got it.
What is the answer?
Option
B.
B. I mean, basically, you cannot change the pixel, otherwise the image itself is changed. However, you can play with the colors in a way that your edges will stay there. However, like let's say your earlier flower was white, but you change the color to red. However, the edges are there, so they will figure out that this is the flower only, right? But if you are simply changing a pixel like such that your the leaf of this flower coming in between and the center is going outside, then this is not flower, right? Like that is the
Correct.
shuffling of pixel in some way. So yeah.
Yeah, pixels, if we change, whole image will change.
Image
Yes.
will change, exactly. Yes.
Image will change, that will no longer be the original thing. So it is not a
It will
data.
confuse the neural network. Mu and
Yes.
sigma.
Uh,
Yeah, exactly.
yeah,
It's
it
is more
not
like
a data.
creating a noise. So noise never helps, right?
Neural network will be unable to learn anything. Yes.
Yeah. Yeah. Let's see question number 9.
The capacity means ability to neural network to approximate the number
Option A,
dropout
Correct.
ratio increases, capacity
Simplest.
increases. As learning rate increases, capacity increases.
Yeah, option A should be correct, right?
Yeah, is correct.
No confusion, right? Yeah. Last question.
But a dropout also increases the capacity, right? No.
But it's but the question is dropout increases the capacity, but the dropout ratio doesn't increase it. You don't know how much dropout ratio is correct one. Like
Okay. Ratio. Thanks. Batch number.
so option A should be correct.
A.
Yeah.
Yeah, great. So I think we understood most of the thing from this week. Yeah, so try to write code, do some uh, do your hands dirty, then only it will be better.
Thank you very much.
Thanks a lot.
Okay, so we will stop recording and yeah, we will